Imagine this is the first day of class. No equations, no exams, no expectation that you already know physics. Just one question. Can the entire universe be explained by a single idea? Physicists call this idea the theory of everything, not because we have it, but because we're still looking for it. Today, we're not going to solve the universe. We're going to understand what a theory of everything would need to explain, and why that turns out to be so difficult. If a theory truly explains everything, it must make sense of space and time, matter and energy, the forces of nature, gravity, the quantum world, black holes, and the beginning of the universe. If even one of these breaks the theory, then the theory isn't complete. So let's start at the foundation, space and time. We usually think of space as a stage, a fixed backdrop where events happen, and time as a ticking clock moving at the same pace for everyone, everywhere. According to Einstein, that picture is wrong. Space and time are not separate things. They are woven together into a single fabric called space-time. Mass and energy bend this fabric, and that bending is what we experience as gravity. Objects don't fall because they're pulled. They fall because space itself is curved. This idea works extraordinarily well. It predicts the motion of planets, the bending of light, and the behavior of entire galaxies. But there is an assumption hidden in this picture. Space-time is treated as smooth and continuous, like an unbroken surface, and that assumption will later collide with quantum physics. Next comes matter. Matter feels solid and permanent, but at its core, it's just structured energy. Atoms, particles, even you, are energy arranged in stable patterns. In fact, most of the matter in the universe doesn't seem to be made of anything we recognize. When astronomers observe galaxies, they rotate as if there's far more matter than we can see. Something invisible is adding extra gravity. This missing mass is called dark matter. We don't know what it's made of. One possible candidate is a hypothetical particle called an axion, extremely light, extremely elusive, and so far undetected. Whether axions exist or not, the evidence is clear. Most matter in the universe is hidden. Energy comes next. Energy is what allows change. Motion, heat, light. All of these are forms of energy. And just like matter, energy turns out to have a dark side. When we observe the expansion of the universe, we find that it's not slowing down, it's speeding up. Something is pushing space itself to expand faster and faster. We call this dark energy. We don't know what dark energy is. It may be a property of space itself, or something even stranger. What we do know is that it dominates the universe. Most of the energy in existence comes from something we barely understand. Now we come to the forces of nature. All interactions in the universe are governed by just a few fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. Three of these forces are described with incredible accuracy by quantum physics. They behave as exchanges of particles, following precise probabilities. At extremely high energies, these forces appear to merge, hinting that they may all be different expressions of a single underlying force. Gravity, however, refuses to fit into this picture. Gravity is not described as a particle exchange in everyday physics. It's described as the shape of space-time itself. When physicists attempt to describe gravity using quantum rules, the mathematics breaks down. This is the central obstacle to a theory of everything. The quantum world is where our intuition truly fails. At very small scales, particles don't have definite positions or paths. They exist as probabilities. Reality behaves more like a set of possibilities than a fixed script. This framework works astonishingly well. It explains chemistry, electronics, and nearly all modern technology. But it treats reality as granular, made of tiny, discrete pieces. That directly contradicts the smooth space-time of relativity. Some theories attempt to bridge this gap. One proposal suggests that the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings. Different vibrations would appear to us as different particles. String theory also requires extra dimensions of space, dimensions we don't experience directly. So far, it remains unproven. It's a mathematical framework, not an experimentally confirmed theory. Other approaches attempt to make space-time itself quantum, breaking it into fundamental units. None of these ideas have yet been confirmed by experiment. The conflict becomes unavoidable in extreme environments. Black holes are regions where gravity becomes overwhelming. Space-time curves so strongly that not even light can escape. At their centers, the equations of relativity predict infinite density. Quantum physics cannot handle infinities. Both theories fail at the same point. The same breakdown occurs at the beginning of the universe. The Big Bang was a moment when the universe was incredibly hot, dense, and small. Gravity and quantum effects were equally important. And yet, we know the Big Bang happened, because the universe still carries a faint echo of that beginning. In every direction we look, we see a weak glow of microwave radiation, the cosmic microwave background. It's the cooled remnant of the early universe, released when space first became transparent to light. This radiation is nearly uniform, with tiny variations that later grew into galaxies and stars. It's one of the strongest pieces of evidence we have that the universe began in a hot, dense state. But without a unified theory, we can't describe the very first instant itself. We can see what happened after, but not the moment where space, time, and physics were born. So what is the theory of everything? It's not a single equation written on a board. It's not a final answer. It's the idea that space-time, matter, energy, forces, gravity, and quantum reality all emerge from something deeper. We don't know what that deeper structure is yet. And that's not a failure, because science is not about certainty. It's about understanding how much we still don't know and continuing to ask the right questions. The theory of everything isn't the end of science. It's the direction. Thank you for watching. I hope this helped make these ideas a little clearer and a little more approachable. See you in the next video.